Thanks, Todd, and I'd like to thank the program committee for letting me talk about my work here today. My name is John Gouwar. As I said, I'm from Northeastern University. I'm a PhD student in the Programming Research Laboratory, and I'm going to talk about our way of speeding up binary installation with splicing. And this is joint work with Greg Becker, Tammy Dahlgren, Nate Hanford, my advisor Arjun Gouwar, and Todd himself. So just a quick acknowledgement of funding. This work was performed mostly while I was an intern at Lawrence Livermore National Lab. So I'm going to start with an uncontroversial statement that Spack is a source-based package manager. And there are a lot of benefits to being a source-based package manager. You get better configurability, access to platform-specific optimizations, bleeding-edge releases since you can just compile source code, robust handling of virtual dependencies, and better reproducibility since everything is handled for you. But there's one big con, and that's the time it takes to compile packages. And we just heard from Kathleen about her attempts to speed up this compilation. But I want to ask, like, what if Spack could compile ahead of time and even avoid recompilation whenever possible? And any seasoned Spack users here might think it can, so I'm done. But I jest, of course, because there are some restrictions. And this restriction is that Spack requires to reuse any binary. It must also reuse the binaries of the dependencies against which it was built. Now, hearing this seems like a totally reasonable restriction. It ensures binary compatibility. It ensures the reproducibility. And perhaps you might not even find it that arduous. But I'm going to provide a few examples in the case when this will lead to superfluous rebuilds and this restriction is too conservative. So let's consider a concrete build of Trilinos here that I've sort of stripped down to 4 key packages, HDF5, zlib, mpitch, and Trilinos. So we have this pre-installed, perhaps in our build cache server, and say we want to deploy it on an HPE Cray cluster. Well, HPE Cray recommends that you use their bespoke MPI implementation, Cray mpitch, and in fact, they take great care to make sure that it is binary compatible with mpitch. So you would hope that you would never have to rebuild this first spec. In order to construct the second, you could simply just relink. However, that pesky restriction from the previous slide means that we actually would have to rebuild HDF5 and Trilinos again, which could take quite a long time. But now we've built this spec, so now it's sitting on our HPE Cray cluster. But perhaps we want to update our zlib dependency with a binary compatible version of zlib. So we'd rebuild that dependency, but we'd hope again that we wouldn't have to build anything else. But sadly, the restriction strikes again. And we end up having to rebuild HDF5 and Trilinos again. And I hope by the end of this talk to describe our mechanism for keeping these rebuilds from happening. So I'm going to refine my previous statement. Spack is really a source-first hybrid package manager. So it manages both from source build and binary distribution, but it is source-first. And as a consequence of being source-first, there are certain implications on the dependency semantics of package configurations. Namely, Spack packages specify their dependencies at the API level, and the definition I'm going to give for API level is it's a source level contract that describes the interface that a library provides. So namely, a client can write source code agnostic of the particular implementation, but it may have to be recompiled if that implementation changes its binary interface. So to see where this source compatibility can lead to problems at the binary level, let's consider an implementation of a point library. So we define an opaque type of points, some operations, adding, subtracting, finding the midpoint, computing the distance between them. And now let's consider 2 implementations of this point struct. The one on the left seems pretty standard. It's struct with a x field and a y field. But the this is verified with GCC on Godbolt using GCC. That ultimately this will have a compiled representation of size 8 bytes on a 64-bit machine. If we consider a perhaps exotic implementation of a point struct where we add another field that perhaps the library is internally caching operations. This would actually lead to a compiled size of 16. So a client could use either implementation of these without changing their source code because it is API compatible. However, once it were compiled against either one of them, it could not use the other. Or if it did, it would lead to undefined behavior because it would be attempting to pass around structs of the wrong size. So the reason we have that restriction from before is that in order to avoid this undefined behavior, Spack assumes that every change can be ABI breaking. Because it's not modeling the ABIs, it's only modeling the APIs at the package level. It has to assume this to avoid undefined behavior. So perhaps the solution is rather obvious. We have to model ABIs. And in fact, we also have to allow specs to be able to represent these heterogeneous binaries, which may have been compiled in one way and deployed in another. So we present splicing as this model of heterogeneous binary reuse that maintains the build provenance of compiled binaries, and then I'll get into the ABI modeling in a little bit. But let's first do a quick tour of the splicing model of reuse. So I have two synthetic specs up here, and we can assume that the specs that have the same letter are binary compatible in this example. So perhaps we have this T spec in the cloud, and on our system we have some optimized version of M, which I'm calling here M prime, sitting on our system. And what we would really like is T with M prime without recompilation. So the representation is actually quite simple. Just put them together. It's not that hard. But one thing to note is that while T and M correspond to extent binaries built by Spack, this combined spec is, which we call spliced together, does not currently represent an extent binary, but a combination of binaries. And if Spack wants to be reproducible, we want to be able to distinguish these sort of Frankenstein binaries from their original. So we just add one back edge to say, hey, look, this binary here is actually derived from this original one that was on the build cache. Now note the shared Z and Z prime dependency. Here we've done what we call a transitive splice, where when we just wanted to splice in M, we ended up replacing Z prime. But in fact, if we just wanted to replace M prime, but we wanted to keep our original version of Z, well, the solution is just another splice. So we splice Z back in, and now we have just our dependency on M prime carrying around this S that it needs as well. And in fact, we still have to carry around our back edges so we know how to derive each of these binaries. Now, this was fairly mechanical that I walked through here, but we've actually automated all of this in the concretizer, provided that you model the ABIs in packaging. So we added one directive to Spack that we're calling can splice, and it has three components. So first are the targets. So these are specs that can be replaced by a splice. So this is on our previous example. This would be the blue M or the blue Z, or the blue and green Z. These can both be the name of the same package or a different package. This is to model a case like when we want to splice something like cray mpitch. And then there's the when spec that describes when the package that we're writing this in conforms to the when spec, it can be replaced for the target with a splice. And finally, we have this match variance field. So this is variance that we care about matching between the two specs, but we don't care about their exact value. So these will be variants that potentially add functionality, like a JSON variant or an MPI variant, where we just need them to be the same, but we don't care about their particular value. So you may be thinking, how can you use splicing today? Well, first is explicit splicing. This is similar to the mechanical presentation that I presented earlier. In your configuration, in your environment, you would say that you like to do an explicit splice. The target is the kind of spec you want to replace. This can be either a concrete spec, a abstract spec, or even a virtual spec. So this would replace every MPI in a concretized environment with cray and pitch. And you can express the transitivity you want. However, be warned, this operation is unsafe. Spack is doing nothing for you to ensure that you don't break your specs here. You have to know whether or not the replacement you specify is ABI compatible. Spack will happily relink for you and can introduce undefined behavior if you're not careful. But there's automatic splicing, which is a little easier. You just turn it on, and Spack will sort of optimally minimize your builds by introducing splices where it's appropriate, depending on what you request. But you do need the relevant can splice directives in packages. So just as a quick conclusion, in order to get the most out of binaries, Spack has to be able to reuse these binaries heterogeneously, so we can build in one place and deploy in another. But we need to make sure that we maintain build provenance, and we need to model package ABIs. Splicing is what lets us model this heterogeneous binary, and can splice is what allows us to model these ABIs. So if you maintain a package that has some sort of binary compatibility, please go in and add can splice. My work this summer will be working to automate some of this, but having developers audit it would be great. And with that, I'm ready for any questions.
Who's got questions? I think do your last slide. Andy.
Hey, thank you. Nice talk. And nice work, whole team. So if I get this right, and this is an insultingly basic question, I've got a package at version XYZ. I release a bug fix version of that, yes. XYZ prime. Mm-hmm. I just put can splice. When I update the package to pick up that new one, mm-hmm. I actually do the can splice in there. And as long as people have got this automatic true set, it will automatically do the minimal damage to pick up that bug fix. If I'm confident that I just fixed a bug, I didn't change a damn thing, I just stopped it screwing up.
Yes, and if you add the can splice, you would add something like the first line. When at 1.1.0, or with a bug patch, I suppose, I can splice into myself at 1.0.
I just want to make sure I got that. Thank you.
Alec.
Yeah, so on the side of package maintainers, do we have any documentation or good way of knowing when a package has ABI compatibility or not, or can we test for that one way or another? I know there's like libabigail that we've used before in build SI, but do you have any recommendations there?
So no, we don't yet have a tool. I hope to build one this summer that will allow developers to generate something a little more regimented. But you could use libabigail. You could string together tools yourself, but I hope to add sort of a Spack porcelain for it.
So this looks great. I have a question. So you mentioned some of this is Spack API, and I'm curious on the relationship here on now that we've done compilers as nodes, and we are starting to relax the requirements for containing like build linked or non-linked dependencies. Do we need to account for that with splicing, or is that separate and that's automatically going to be taken care of? Because theoretically, there's a whole section historically of reusable builds that have happened just because of build time dependencies that aren't actually in the link run graph.
So I guess can you clarify what you mean by that? I guess I'm.
Yeah, so currently the solver, when determining whether it can reuse an already built thing, doesn't consider the build dependencies at all. So the splicing algorithm that John worked on last summer just leaves the build dependencies out entirely, because if you're using a spliced thing, you're only using it from a build cache. You just don't consider the build dependencies at all. And he talked about the back pointers to the way it was built. You can always go look up what they were when you built it.
Any other questions? Okay.
This match variance thing, does that only work for splicing, or can you use it for regular dependencies or requirements, conflicts, that sort of thing?
This is special case to can splice right now.
Some of this may be replaced with another syntax that we're working on for being a little more expressive. Any other questions? I have a question. Do you think this metadata is best represented in the package.py or on the binary?
So what do you mean by on the binary? Because
So
the way I think about it is the package.py is your one-stop shop for everything that is possible with a particular package.
Yes. So what I mean is for Andy's use case, right? Like suppose that I have an old version of Spack and I haven't updated my package.pys, right? There may be a new binary that comes out from somebody that's spliceable, and I might want to know that it's spliceable, and I might not want to have to update my packages to know that. And so if, I don't know, at build time we concretize this onto the binary, then you could know what a package could replace just based on its own metadata, as opposed to having to refer to the package.py.
Wouldn't you then have to pull the binary though to figure out if it's binary?
The metadata, which is actually separate. There's a signed manifest for that that's separate.
Package.py is already in the metadata, so we already.
Yeah.
So
Yeah.
this may be a leading question, but that's like that's sort of what Geeks does with
Yes.
graphs. So potentially, but I think explicit splicing is really the interface for that. Is it sort of a stopgap when you do something quick like that? You can fix it quick, and then eventually you roll it into the can splice, and then that fixes it forever.
Okay, let's have a technical discussion before this summer. But yeah, any other questions on this one? Okay, wow, 2 more. Okay, how much time do we have? Actually, we're out of time for questions, so you guys ask him
I'm happy
later.
to talk offline. I'll be here for the rest of the
Psych.
comment.